All right, let's go over some questions from exam 3, the multiple choice questions. So question 1, we have dipoles. Which dipole vector is best reflected on the molecule provided for ibuprofen? So dipole is the net dipole moment of a molecule is the sum of bond dipole moments. So if you look at option A, what we have is the CO bond dipole moment over here, not the net dipole moment. And then in option B, we have again the C double bond O net dipole moment, the C double bond O bond dipole moment, not the net dipole moment. And then option D goes the other way, because what we have here is we have one bond dipole moment going this way, the other one going somewhere around, let's say, I mean, if we have the hydrogen like this, it should go like this. Anyway, so if you just neglect the hydrogen for the moment, OH bond for the moment, because it is rotating, we can consider that the bond dipole moment for CO like that, and then based on that, at least it should be between the arrowhead must be within this region. Okay, but in option D, the arrowhead is going the other way around. Therefore, we will discard option D as well. Okay, and then based on all the options, the best option is option C. Why? Because we have our arrowhead between the two oxygen atoms over here, because those are the more electronegative atoms. That means they're going to get the partial negative charge, and then the partial negative charge means the arrowhead is should be between them. So for that reason, the best one would be this option C. All the others are not as good as option C. Okay. All right. Now moving on to question 2, which best reflects the dispersion forces that could be present between two molecules of ibuprofen. Now option A is out, because option A is showing us dipole-dipole interactions, so dipole-dipole forces. And then option B, we have the electron cloud indicated. Partial positive charge of one molecule is interacting with the partial negative charge of the other, and then so forth. And this seems very good. And option C doesn't seem correct, because we have two partial positive charges close to each other. That is, they repel, they do not attract. And the same thing over here in option D, the same partial charges should not be attracted to each other, they repel each other. Yeah, for option C and D are out as well. The correct answer is option B. Question 3, identify the bond angles for the atoms indicated in the line structure. We have A, B, and C atoms. So in A, what we have is a bend. So bend is a carbon, and then we have a hydrogen, carbon-hydrogen bond to fulfill the common bonding pattern of carbon. And the question is the bond angle. What we have is 3 electron domains. All of these electron domains are bonding electron domains. Therefore, they are going to arrange in a trigonoplanar geometry in space to minimize the repulsions between them when it comes to these electron domains. And if you look at the angle between them, the angle should be 120. Okay, so all of them have 120, so it doesn't help. And then what we can do is we can look at option B. So option B, what we have is we have 2 lone pairs. So the electron domain geometry is tetrahedral. But we because we have 2 lone pairs and then 2 bonding electron pairs, and then if you look at just the bonds, we have 2 bonds, so 2 bonding electron domains, and they're going to arrange in a bent geometry, and the bond angle should be less than 109, 109.5. Okay, so we are going to eliminate options A, C, and we are left with options B and D, because both of them have a bond angle of less than 109 or 109.5. And then the last one here is a nitrogen. Again, we have a lone pair to fulfill the octet around this nitrogen. and therefore we have 4 electron domains. Therefore, it's going to be a tetrahedral electron domain geometry. But if you consider just the bonds, they're going to arrange in trigonal pyramidal geometry. And then if it was a perfect tetrahedral geometry, the bond angle should be 109.5 degrees, but this lone pair is taking up more space. It's going to pinch the bond angle a little bit. Therefore, the bond angle will be a little bit less than 109.5, and then that would be option D. So therefore, the correct answer for this question must be option D. All right, moving on to question 4. Rank these bonds in adrenaline in the order of increase in polarity. So in all cases, CC bond is the least polar bond because it has no electronegativity difference, because bond polarity depends on the electronegativity difference mainly, right? And then that doesn't help. And then we need to consider the electronegativity differences. Let me see that. So oxygen is 3.5, hydrogen is 2.1, and nitrogen is 2.5, and hydrogen is 2.1. We need to write them separately, otherwise we're not gonna write here. Give me a second. Okay, so let's do CO, NH, and OH bonds. Okay, oxygen is 3.5, carbon is 2.5, nitrogen is I think nitrogen is from 3.0, hydrogen is 2.1, oxygen is 3.5, and then hydrogen is 2.1. So the electronegativity difference, so delta chi for CO bond is around 1.0, and for nitrogen, hydrogen should be around 0.9, and then for OH bond, it is around 1.4. So the most polar bond out of these polar bonds should be the OH bond. Therefore, we can eliminate options D and C, because OH needs to be the most polar bond. And then just before that, it should be the CO bond. Okay, so we will give any electronegativity values. Let me check for the nitrogen. Nitrogen is 3.0. Okay, now anyway, moving on to this. So the correct answer must be option B, because NH has a 0.9 electronegativity difference, while CO has 1.0 electronegativity difference. Because we have a great electronegativity difference in CO bond must be polar, must be more polar than the NH bond. All right, so with that, let me erase these guys. Okay, and question 5, what functional groups are present in this molecule? Okay, so we are talking about this molecule over here. So in this molecule, we have hydroxyl groups, amine groups, and a phenyl group. So we have hydroxyl, amine, and phenyl. We have all three. Okay, that's what I would go with. Therefore, option D. Question 6. What is the molecular and electron pair geometry of these molecules? We are given SO2 and NO3 minus. So if for SO2, if you draw one of the Lewis structures, because it has resonance, you can draw two Lewis structures for this, or resonance structures for this. It's going to look something like this. Okay, and you have 3 electron domains, 1 lone pair, 1 single bond, and 1 double bond, and they're going to arrange in a trigonal plane geometry. Okay, so the electron domain geometry must be trigonal planar, and then the molecular geometry, the shape of the molecule, is going to be bent. Okay, so that leaves us with trigonal planar bent. So we can eliminate options B and options D. Okay, and now moving on to NO3 minus. Okay, and NO3 minus. Yeah, let's do the Lewis structure first. Okay, just to make sure everybody's on the same page here. So nitrogen has 5 electrons, oxygen has 6 valence electrons, that we have 3 of them, therefore 18 electrons, and minus 1 charge is 1 electron. Altogether we have 24 electrons, that means 12 electron pairs. Okay, and therefore they are going to arrange, and if you draw the skeleton, it's going to look like this. And if you distribute the 12 electron pairs, we already distributed 3 electron pairs here as bonds between nitrogen and oxygen. 1 2 3 4 5 6 7 8 9 10 11 12. Okay, now all our oxygens have an octet, but nitrogen does not have an octet, so we can delocalize from one of these oxygens. So we can have 3 options, so 3 resonance structures. So anyway, so if we do that, let me do this over here for the sake of space. We're gonna get something like this. So we have 3 electron domains. Now for the electron domain, geometry should be again trigonal planar. And then the molecular geometry is also trigonal planar, because all our electron domains are bonding electron domains. Now for the correct answer is option A. All right, moving on to question 7. We are given 40 electron spectra. What can be said of the electrons bonded between X and Y? So anyway, so here's the X and Y bond, and we see that we have a higher ionization energy for X electrons compared to Y electrons. Therefore, that means we have a lower potential energy there, because electrons are strongly attracted to X nucleus compared to the Y nucleus, and that's why we have a higher ionization energy. That means higher energy to remove electrons in X compared to Y. And as a result of that, when the bond is formed, this bonding electrons will spend more time around X rather than Y. Okay, in other words, X is going to be more electronegative than Y. Okay, so X will be partially negative, Y will be partially positive. Electrons spend more time near X because valence shells in X have a lower potential energy. That is absolutely correct. Remember, lower potential energy means stronger attractive interactions. Okay, because electrons, because X has a higher ionization energy in the valence electrons, meaning these valence electrons are more strongly attracted to the X nucleus. Therefore, it's going to have a lower potential energy. Stronger the attractive interactions, the lower the potential energy. Option A seems to be seems to be correct. Option B, the electrons spend more time near X because the valence shells in Y have low. No, that is not correct. The electrons spend more time near Y. Nope. The electrons spend more time near Y. Nope. So yeah, the correct answer is option A. Moving on to question 8. What can you predict about the relative volatility of the 2 substances? Oh, okay. So we have one here, another one here. Okay, both of them are polar because we have this carbon sulfur hydrogen bonds over here. Anyway, because of the SH group. Anyway, and also the structure B is more polar because we have this extra nitrogen here as well. And remember, even though we drew it like this, the bond dipole moments, this SH bond or carbon sulfur bond is a single bond, therefore they cannot rotate. Therefore, it's not gonna stay like that. The idea is we have more electronegative atoms in B, therefore it's gonna have more polar, more dipole-dipole interactions. Okay, and also structure B has more electrons, and therefore it's gonna have stronger dispersion forces. And also structure B has more trigonal planar carbons in this ring. Okay, and more trigonal planar carbons mean they are going to have a greater surface area of contact because planar structures can stack like pancakes. Anyway, so structure B should be less volatile, in other words, because it has stronger overall intermolecular forces. Let's read the option. Structure A will be more volatile. That is true, because it has weak intermolecular forces. That is correct. Structure A will be less volatile. No, it's going to be more volatile because it has weaker intermolecular forces. Structure B will be more volatile. That is incorrect. Structure B will be less volatile. That is correct, because it has weaker intermolecular forces. No. If something is less volatile, that means it should have strong intermolecular forces. Anyway, the correct answer is option A. All right, moving on to question 9. Rank these substances in order of increasing polarizability. Polarizability is all about the number of electrons, and then the volume these electrons are in, right? And out of 1, 2, and 3, we can see that on all of them has 1 seems to be the smallest structure, and even though option 3 lacks a sulfur atom, which has about, can go here, sulfur atomic number is 16. That means it has 16 electrons. Okay, so even though it does not have the 16 electrons from sulfur, because it has more carbon atoms, like here, let's say we have 1, 2, 3, 4 carbons and 1 sulfur, and then some hydrogens here. But in option 3, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons, and each carbon atom brings 6 electrons each. Therefore, because of having 6 more carbons, the lack of sulfur is compensated there. Okay, anyway, the point is the molecule 1 has the lowest number of electrons, and it is the smallest. Therefore, it's going to be the least polarizable out of 3. Okay, so lowest polarizability should be 1. Oh, there's only one answer with the lowest polarizability. Okay, and then 3, and then 2 will be the most polarizable. Why? It has the most number of electrons, because on top of having 10 carbon atoms, it also has sulfur as well. And then because of that, we can say that it is going to be the most polarizable. That is true. Okay, so anyway, based on the least polarizable molecule, the correct option has to be option A. All right, moving on to question 10. What is the most likely reasoning for the boiling temperatures provided? We have 186 for the molecule A, 265 for molecule B. We see that we have more hydrogen bonding sites. Okay, we have like 1, 2, 3, 4, 5 hydrogen bonding sites in molecule B compared to only 2 in molecule A. Okay, that's 1. And then also, because it has more electronegative atoms, it's going to be more polar. That means it's going to have stronger dipole forces as well. And on top of that, I would say that it has more electrons as well, because of this extra. No, maybe not. Anyway, so it's going to have more hydrogen bonding sites and then more dipole interactions. Therefore, I mean, the higher boiling point must be justified. It's just justified with that alone. Because if you have a higher boiling point, that means it's going to have stronger intermolecular forces, and the stronger intermolecular forces are justified because it has more hydrogen bonding sites and more dipole interactions. All right, anyway, molecule B has stronger intermolecular forces because it has additional regions where hydrogen bonding interactions can occur. That is absolutely correct. Molecule A has stronger intermolecular forces is incorrect. Molecule B has strong intermolecular forces because it has stronger dispersion forces. No, that is not valid. Because in molecule A we have sulfur, which is bringing a lot of electrons. Okay, In molecule B, in lieu of that, we have an oxygen here, and then we have this another oxygen over here. So it will have more or less the same number of electrons if we count that. Okay, so and then if you move on to option D, molecule A has strong intermolecular forces is incorrect, because if it had strong intermolecular forces, it should have a higher boiling point. All right, moving on to question 11. Sometimes when we get stressed, blah, 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 to the right is the PEG diagram based on the mixing of La with AA, the major components in vinegar. Based on the PEG diagram, what is true of the mixing of these substances? You see the mixed state has a lower number of configurations and a higher potential energy, right? Meaning both potential energy and the number of configurations do not favor the mixed state. This is going to be insoluble at all temperatures. So that's it. They will be miscible. No, they will be immiscible at all temperatures. That is option B. They will be miscible. No, okay, this is going to be immiscible at all temperatures, because both potential energy and the number of configurations do not favor the mixed state. Moving on to question 12, used in the PEG diagram, the previous question, what is true for the relative intermolecular forces of these substances? In the mixed state, we have LAAA interactions, LAAA in the mixed state, okay? And in the unmixed state, we have LL and then AA interactions. Okay. Now, because the unmixed state has a lower potential energy, meaning it should have stronger overall intermolecular forces, stronger interactions. Therefore, LL interactions and AA interactions must be stronger than LAAA interactions. Okay, let's read the options. LAA interactions are, no, that is not correct. Okay, this is the mixed state. LA interactions are weaker than LA. Okay. All right. Yeah, so this should be LA. Anyway, LA and AA interactions. That is correct. Option B is correct. LA, AA interactions are the same. No, this is impossible to determine. That is not correct. Okay, so option B is correct. Okay, LA, AA interactions, or the interactions in the mixed state, are weaker because it has a higher potential energy compared to the interaction in the unmixed state. All right, which of the following polymers would be most rigid? Most rigid means stronger IMFs. Okay, so all right, so I would go with option C. Okay, why? First of all, compared to option A, it is longer because you have only 100 repeat units in A, and in C we have 500 of them, which is longer. Longer means you're going to have a greater surface area of contact, and also has more electrons. It's going to be more polarizable, therefore stronger dispersion forces. And then I avoided, so then also I'm gonna eliminate option D as well. Option D should have the weakest, because on top of having a shorter chain, it has branching as well, which is going to act as barriers for the molecules to come close to each other. Okay, and as a result of that, it's going to have weaker. It's going to have lesser surface area of contact. Therefore, it's going to have weaker intermolecular forces. And option B, even though it has 500 residues, this branching is going to act as barriers for the molecules to come closer to each other, reducing the surface area of contact. Therefore, the intermolecular forces are weakened. Okay, therefore the correct answer is option C. For the most rigid, strongest intermolecular forces, strongest. All right. Moving on to question 14, which would decrease the rigidity of a polymer. So if you want to decrease the rigidity of the polymer, you need to weaken the intermolecular forces. Adding cross links will strengthen the intermolecular forces. That's not going to help. Adding branches will decrease the surface area of contact, thereby decrease or weaken the intermolecular forces. That is correct. And the hydroxyl group will provide hydrogen bonding sites, and then it will make the polymer more polar, making the dipole-dipole interaction stronger as well. Therefore, that is incorrect. So option, we can only do 2. So it's going to be B on 2 only. Question 15. What would be the monomer that would produce the copolymer A? So the copolymer A is this guy over here. So if you take that out, what we see is this part is repeated over and over. Okay, so I took out the parentheses, and instead of drawing these 2 bonds coming out through the parentheses, I'm going to draw a double bond. Therefore, this should be our monomer. And that looks like option A, right? Yeah, it cannot be this, it cannot be this, because there are no double bonds. And then D seems to have more carbon atoms than needed. Therefore, option A is correct. This is the correct answer. Question 16. Which copolymer would you predict to have the strongest interactions and produce the most rigid polymer, and why? Okay. So let's see. All right. Now, what we see is, it is true that copolymer B is out. Okay, because even though it has this trigonal planar carbon atoms, all right, it does not have anything else going on for that. Now, because in copolymer A, we have the CN group, which is polar. Now, it's going to have dipole-dipole interactions. Okay, and then carbon has 6 electrons, nitrogen has 7 electrons. Therefore, we have 13 electrons there. Okay, so that is something to think about. On the other hand, if you consider copolymer C, we have 6 carbons, that is 6 times 6, 36 electrons, plus 5 electrons from the hydrogen. Therefore, altogether 41 electrons. Okay, so 41 minus 13 is, let's say, 21, 28 or something like that. So something like 20, yeah, I would say 28 electrons more than this polar group, because it has more electrons. Okay, I mean, we talked about this 15 electron rule, which is, we said it's a fake rule. It helps us predict when dispersion forces can outweigh the dipole-dipole forces. So here's one such situation. We have a lot more electrons in copolymer C because of the prenyl group, and therefore it's going to have much more stronger dispersion forces. And also it has this planar geometry going on, which helps the molecules to stack on top of each other. Therefore, it's going to have overall stronger intermolecular forces. Okay, so polymer A should be out. It should be copolymer C, because prenyl group is planar and highly polarizable. That is absolutely good. And copolymer C, because the prenyl group has dipole. No, prenyl groups does not have dipole-dipole interactions because it is not a polar group. All right, so yeah, those are the answers for the multiple choice questions. I hope this helps. I'll see you guys in class. Bye, everybody.